Hi everyone, we are talking about a different integration technique called integration by parts. It works really well if you have a product of two functions, especially where the derivative of one of them will go down to zero and the derivative of the other one will kind of cycle. Okay, so like e to the x, the derivative just remains e to the x for forever. Sine of x, it cycles, natural log, it'll never hit zero because you'll go 1 over x, then negative 1 over x squared, then so on. Right, so first let's derive it. So if I'm multiplying two functions together, right, we have to use product rule if we wanted to take the derivative. So the way that we could write that would be u dv dx plus v du dx, okay, where dv dx is just the derivative of v. Okay, now if I wanted to integrate both sides, okay, if I wanted to integrate, then just do this. Then the integral of uv will, the derivative and the integral kind of cancel, so we just have uv here. And this would be equal to, you can write this as u dv plus v du. Okay, the dx's just went over here, canceled out. Okay. So now if I just rearrange this, now keep in mind that this is the same thing as the integral of u dv plus the integral of v du. Remember our integral rules, we can split up a sum or a difference. All right, so if I rearrange this, then I can get the integral of u dv to equal uv minus the integral of v du. All right, you might ask like why this is helpful. So in a situation like this, where you have a product of two functions, this we can't integrate the way that it is. So we will need to rewrite it some way, right? And that's where integration by parts comes into play. So while it may not look very helpful at first, okay, once we go through an example or two, you'll kind of see why we do this. All right, so here's our formula. The integral of u dv equals uv minus the integral of v du. All right, so let's try one. Let's do x sine of x. Okay. So the first thing we have to do is establish a u and a dv. All right, we're gonna pick those. Okay, we split this up. Now what I'm looking for u is something easy to differentiate. All right, so it's better if what I pick for u will actually go down to zero if I take the derivative enough times. All right, so what I'm going to pick for u is x, and whatever else goes for dv. So sine of x dx is going to go right here. All right, so I just split it up into u and dv. So this is my u, this is my dv. So I have the integral of u dv, which is the left side of my formula. Okay, now I have to figure out what du is and what v is. All right, well for du, I just take the derivative of both sides. So the derivative here is going to be dx. Okay, the derivative of x is 1, and then I have a dx here. To find v from dv, I'm going to have to take the integral of both sides. So the integral of sine with respect to x is negative cosine. Okay, so now I'm just going to rewrite. Remember, this integration by parts doesn't actually do the integral for us. It just rewrites it in a way where we can do the integral. So first I have to do uv, so negative x cosine of x minus the integral of v du. Right, so negative cosine of x dx. Okay, so I'm just going to bring this negative out, make that a plus. And now you'll notice, now this integral is doable. Hey, I can do this, and the product, or the complicated part, is out here. I'm not doing the integral of this, I'm doing the integral of this. So the fact that this is still complicated is fine. This is now much easier. The integral of cosine is sine plus c, and we're done. All right, so what integration by parts did is it just rewrote our formula in a way where we actually can take the integral. All right, let's do another one. So here, you can probably guess what we're going to do. Sometimes you have to do it twice. So first, I'm going to establish a u and a dv. Right, so for my u, again, I'm going to pick something easy to differentiate, something that will eventually go down to zero if I take the derivative enough times. I don't want something cyclical here, right? So for dv, I pick e to the x dx. The integral of e to the x dx is e to the x, very easy. The derivative of x squared is 2x dx. All right, so first uv. So x squared e to the x minus the integral of v du. So 2x e to the x dx. Okay. Now we made some progress because x squared is now x, but I'm going to want to do it again actually. Okay, so this is still something that I cannot integrate. I still have a product here, so I just want to do it again. All right, so again, I define a u and a dv. Right, I'm going to let u be, if you want to bring this 2 out, that's fine. I'm just going to define u to be 2x and dv to be e to the x dx. So v would be e to the x, du would be 2 dx. Right, and now we'll rewrite this again. So x squared e to the x is just going to kind of chill there, minus. Right, now I have my new uv, so 2x e to the x minus the integral of v du. So I'll put the 2 out here, e to the x dx. Now keep in mind, look that I did parentheses here because this negative will affect both terms. Okay, so it's very important to make sure you have parentheses here. Okay, now I do not have a product in my integral. Now I actually can integrate this very easily. So we'll go ahead and evaluate. And you know what? I'll come down here since I have so much room. So this is equal to x squared e to the x just chills minus 2x e to the x plus 2 e to the x plus c. All right, so I distributed my negative to both terms and I integrated, and that was it. Okay, now we're going to move on to something called the tabular method, which is the same thing as just another way of writing it, and can be a little quicker. So this works very well, especially, again, if one of your functions goes down to 0. You actually need that to happen for the tabular method. So what I'm going to do is, again, define a u and a dv. Hey, for u, I establish it to be x squared. For dv, I establish it to be the other thing. Right, now I'm going to keep differentiating this side until I hit 0. So I get 2 to the x, the derivative of 2 to the x is 2, the derivative of 2 is 0, and then I stop. Okay, now for every step that I differentiated, I'm going to integrate. So the integral of e to the x is e to the x, the integral of e to the x is e to the x, and then e to the x. Right, so you need something here that will keep integrating very easily. You need something here that will differentiate down to 0. Now what you do is you alternate signs, so it's going to be a minus, a plus, and a minus, and then you connect diagonally. Right, so what I mean by that is first we have x squared e to the x minus 2x e to the x plus 2e to the x, and then plus c at the end, and we're done. Okay, so we didn't actually have to do all the integrals, rewrite it all. Okay, the tabular method is very fast, but it only works if your u will go down to 0. Okay. Okay, so now what do we do if we have a definite integral? So first, you're going to go ahead and go through the integration by parts as if you did not have limits. And then when you get to the point where you integrate, you just plug them in. Okay, so we already did this problem on the front. So if you look at what we did there, okay, our final, when we took the integral and all that, we got to negative x cosine of x plus sine of x. And then we had a plus c there, but we're not going to put that because this is a definite integral. Okay, at this point, when we're done integrating, when the integral is gone, because I've evaluated it, that's when we're going to plug in our bounds. Okay, so we get negative pi over 2 times 0 plus 1. Okay, so this is plugging in pi over 2 minus 0 plus 0. Right, so we end up getting 1 for our final answer. Okay, so you go through the process of integration by parts until you get to the end when you actually evaluate the integral, and you do integration by parts as many times as you need to, and then you plug in your bounds. Okay, now what happens if I have two transcendental functions? What I mean by that is what happens if I have two functions, neither of which the derivative goes down to 0 like I said you want? Well, if this is the case, you always let the trig function be dv. Alright, so let's work through it. First, I need to define my u and my dv again. So I'm going to always let dv be my trig function. I'm going to let u be e to the x. That means du is e to the x dx. V is going to be the integral here, so 1/2 sine of 2x. Okay, so now I'm going to rewrite this, uv. So 1/2 e to the x sine of 2x minus v du. So I'll put the 1/2 on the outside. E to the x sine of 2x dx. Okay, now we need to do it again. Okay, it doesn't look like we accomplished very much here. So because of this situation, I'm going to again define u and dv. So again, I'm going to let dv be my trig function. I'll let u be the rest of it. So that means du is e to the x dx again. V is going to be negative 1/2 cosine of 2x dx. Okay. So we will rewrite this again. And I'll go down here because there's more space. So 1/2 e to the x sine of 2x, again, doesn't do anything. Okay, I'm not doing anything to that. That's fine the way it is. Minus 1/2, parentheses, okay, because I'm substituting from my integral here. uv, so negative 1/2 e to the x cosine of 2x. Actually, I didn't need this right here. Minus the integral of v du. So I'll put a plus, put the 1/2 on the outside. Okay, e to the x cosine of 2x dx. Okay, now it looks like we're just going to go around in circles because nothing's getting better with this. But notice what I have here, what I have here. Okay, so I'm going to erase this just for space. But keep in mind the original problem. Okay, that's kind of the big trick about doing these. Okay, keep in mind that all of this is still equal to the integral of e to the x cosine of 2x dx. Okay, so I'm going to simplify this side a little bit. Okay, I'm just going to distribute this 1/2, so plus 1/4 e to the x cosine of 2x minus 1/4 integral e to the x cosine of 2x dx. Okay, so all I did was I distributed my negative 1/2. Okay, now I notice that I have like terms. Okay, and I just need to combine my like terms. Okay, the integral is the complicated part of this problem, but if I can bring my integral to the other side of the equation, which I can, because they are the same integral, so it's okay. Then I just have 5/4 integral of e to the x cosine of 2x dx is equal to 1/2 e to the x, sorry, that's a sine of 2x plus 1/4 e to the x cosine of 2x. Okay, so we're treating our whole integral like a variable, okay, like a normal variable. Now I need to get my integral by itself, so I'm going to multiply both sides by 4/5. And so my final answer is the integral of e to the x cosine of 2x dx is equal to, we'll just multiply. So I guess we get 2/10 here, sorry, 2/5. E to the x sine of 2x plus 1/5 e to the x cosine of 2x. And because we did take an integral, I need to stick a plus c at the end. Alright, so this is pretty complicated. I don't think you'll see anything this hard on one of my tests or on the AP test, but if you do see a problem where you have two transcendental functions, you are going to have to do a little bit of reorganizing. Alright, that's it for this. See y'all later.